Welcome to the Advanced Design Workshop on the design of filter strips and bioslopes. GDOT's stormwater program includes requirements for post-construction stormwater management on projects located within MS4 areas. This presentation will discuss two of GDOT's approved post-construction stormwater BMPs, filter strips and bioslopes. Why are we here? Chapter 10 of GDOT's Manual on Drainage Design for Highways includes several different post-construction BMPs that can be used to meet GDOT's MS4 permit requirements. In this presentation, we will go into detail about the use of filter strips and bioslopes to meet GDOT's post-construction stormwater requirements, including purpose, function and components, design considerations, advantages and disadvantages of their use, sizing and design of the BMPs, and design examples to demonstrate the methodology for appropriately sizing the BMPs as outlined in GDOT's Drainage Manual. We'll begin this workshop by reviewing filter strips. So what is a filter strip? A filter strip is a uniformly graded and densely vegetated conveyance that provides sheet flow, resulting in pollutant removal from stormwater runoff through vegetative filtering. Filter strips also provide some infiltration. A typical grass shoulder in a rural roadway cross-section can often be used as a filter strip. The area should be uniformly sloped and densely vegetated, and typically is 25 feet to 50 feet in length, measured perpendicular to the roadway. Filter strip slope should be between 2% and 25% as measured perpendicular to the roadway. The primary treatment mechanism for a filter strip is vegetative filtration. Filter strips are most applicable in a rural roadway cross-section where they are constructed adjacent to the roadway shoulder along non-curb and gutter sections. Filter strips are often used in series with other BMPs because they do not provide 80% TSS removal, and they do not provide detention. In addition, filter strips only provide a 25% credit for runoff reduction. Some design considerations. Maintaining sheet flow is imperative for this BMP, so the area should be sloped as flat as allowable by site conditions. The slope should be minimized at top and toe of the slope to encourage sheet flow before and after the filter strip. Level spreaders can be used to maintain sheet flow conditions. Filter strips have a minimum length of 15 feet as measured perpendicular from the roadway. But since this BMP works through vegetative filtering, 25 feet or greater length is preferred. The recommended maximum strip length is 48 feet. Remember, a typical grass shoulder in a rural roadway cross-section can often be used as a filter strip if it can be sized to meet these design considerations. Some other considerations. Water quality performance is directly related to the density of vegetation along the strip. Also, because sheet flow and uniform sloping are important, Type 1 turf reinforcement matting is recommended to be installed along with the site's permanent grassing to ensure slopes do not erode prior to establishment of vegetation. Grassing and turf reinforcement guidance can be found in GDOT Specification, Section 700. As we mentioned earlier, sheet flow is a requirement for this BMP to properly function, so your filter strip slope parallel to the roadway should be consistent with the roadway topography. Level spreaders or pea gravel diaphragms can be installed at the top of the slope in conjunction with your filter strip to ensure sheet flow is maintained. Level spreaders for MS4 applications are appropriate to return concentrated flows to sheet flow conditions where the 10-year 24-hour peak flow is less than 5 cubic feet per second. In regards to sheet flow, GDOT has an outfall level exclusion that can waive MS4 BMP requirements. Outfall exclusion number 4 applies to stormwater discharges that exit the right-of-way as sheet flows. If sheet flow can be maintained as it leaves the right-of-way and does not immediately channelize after leaving the right-of-way, then outfall exclusion number 4 may apply to your project. If a ditch is visible in the cross-section, it is likely that this exclusion is not appropriate for the basin. Outfall level exclusion number 4 will need to be approved by GDOT if runoff channelizes outside GDOT right-of-way. Filter strips, when installed as an MS4 BMP, become GDOT assets and require ongoing inspection and maintenance. So during the design process, the designer should ensure that adequate area is provided that allows for safe roadway entrance and exit for vehicles performing BMP maintenance activities and inspections. In summary, filter strips can be an effective, low-cost BMP that easily fits within a roadway drainage setting. However, they are very sensitive to concentrated flow and erosion and may require additional right-of-way to provide the required design lengths. They must also be used in conjunction with another BMP, such as OGFC or grass channels, to meet the treatment requirements. Next, let's review the design process for a filter strip. In the December 2017 edition of the GDOT Drainage Manual, the design process for filter strips was simplified. GDOT included in this manual update a lookup table that provides filter strip sizing requirements based on pavement width and filter strip slope. The values in this table were calculated to provide a contact time of 5 minutes within the filter strip. This table can be used for filter strip sizing as long as the width of the filter strip, parallel to the roadway, matches the pavement length with corresponding slope, and stormwater sheet flows directly onto the filter strip from the roadway. When using this lookup table, the steepest portion of the filter strip slope should be used. For example, if a roadway shoulder has a 6% slope that transitions to a 4:1 slope, the designer should plan for a filter strip length, as measured perpendicular to the roadway, that meets the requirement for a 4:1 slope. Let's review an example project. For this example, we have a 24-foot roadway with a 6-foot paved shoulder and no offside or bypass runoff. This gives us a total pavement width of 30 feet. The roadway drains via sheet flow onto an unpaved shoulder slope of 4 feet at a 6% slope. This drains to a 4:1 shoulder foreslope. Since the drainage area has no off-site flow and drains via sheet flow, the lookup table can be used. To find the required filter strip length, we find 30-foot pavement width and the maximum shoulder slope of 4:1 in the filter strip sizing table, and determine that a 36-foot length is required. Next, let's review the Bioslope BMP. So, what is a bioslope? Bioslopes are filtration BMPs that are typically installed in roadway slopes or embankments. A special media allows sheet flow from the roadway to rapidly infiltrate and filter through the bioslope. After being filtered by the media, stormwater flows are collected and conveyed by an underdrain that is installed parallel to the roadway. A cross-section of a bioslope shows the typical location of the BMP. A strip of grass should be specified directly upstream of the bioslope if space allows. This recommended grass filter strip serves to capture sediment and debris and prevents premature clogging of the bioslope. The pre-treatment filter strip for a bioslope is not designed to the same criteria as the filter strip BMP we just reviewed. Bioslopes are most applicable in rural roadway cross-section, where they are constructed adjacent to the roadway shoulder along non-curb and gutter sections. Bioslopes combine the benefits of filter strips and dry enhanced swales, providing cost-effective treatment in areas where it is challenging to implement other BMPs. Bioslopes provide effective water quality treatment and are rated at 85% TSS removal. They can provide some runoff reduction and are rated at 25 to 50% based on the underlying hydrologic soil group. Bioslopes should be laid out where their length is equal to the length of roadway being treated. The slope perpendicular to the bioslope should be 3:1 or flatter, and the longitudinal slope should be less than or equal to 5%. Ideally, the edge of pavement is less than 30 feet from the bioslope. Additionally, since bioslopes can provide infiltration, a 2-foot separation between the bottom bioslope and the seasonal high water table is required. Pre-treatment is recommended in the form of a grass strip or pea gravel diaphragm. Pre-treatment can both prevent clogging of the bioslope media and can help maintain sheet flow into the BMP. grass filter strips should have a minimum width of 4 feet. Since bioslopes are filtration BMPs, good vegetative cover is imperative. GDOT Special Provision 169 should be used to select sod for the bioslope surface. The sod should be specified to be grown in primarily sand, sandy loam soils with less than 6% clay content. Sod shall be half-cut or thin-cut to promote infiltration, and the sod shall consist of at least 75% of the designated grass species specified in the plans. The top 3 inches of the bioslope should consist of an engineered topsoil mix. Use an engineered topsoil mix that meets the requirements outlined in Special Provision 169, which covers post-construction stormwater BMP items. Topsoil should be obtained from sources approved by the engineer. Bioslope media is comprised of a mixture of crushed rock, dolomite, gypsum, and perlite. The crushed rock provides structure to the media, while the dolomite and gypsum promote the removal of heavy metals from runoff, and the perlite enhances moisture retention. The media should have a minimum depth of 12 inches and should be at least 2 feet wide. The media mixture is designed for an initial infiltration capacity of 50 inches per hour, with a long-term infiltration capacity of 28 inches per hour. The bioslope should be sized using an infiltration rate of 10 inches per hour as a factor of safety. More information on media can be found in Special Provision 169. An underdrain should be specified in the bioslope design to collect and convey the stormwater that has filtered through the media. The underdrain pipe should be perforated polyethylene, sized to convey the design flow, typically the water quality volume peak flow, but should be no less than 8 inches in diameter. The bioslope underdrain should outfall directly to a stable outlet or be connected to an existing or proposed storm drainage structure. The aggregate surrounding the underdrain should be comprised of number 57 stone. Underdrains designed for bioslopes may be significantly longer than those in other BMPs. See Underdrain Special Construction Detail for more information. Bioslopes, like all MS4 BMPs, are GDOT assets and require ongoing inspection and maintenance, so during the design process, the designer should ensure that adequate right-of-way or easement is provided that allows for safe roadway entrance and exit for vehicles performing BMP maintenance activities and inspections. Additionally, bioslopes should be marked with BMP signage so bioslopes are not mistaken as common grassed shoulder. Some advantages of bioslopes are that they provide good water quality treatment and provide some infiltration if underlying soils allow. They are good practices to use in a rural cross-section where stormwater sheet flows from the roadway. Disadvantages are they cannot be used in steep terrain and they do not typically provide detention, so another BMP may be required in series if your project needs detention. For some sites, a bioslope may be sized for the channel protection volume instead of the water quality volume. With this larger design flow, the BMP size would also increase, so available right-of-way may be an inhibitor for this application. Now, let's review the process for designing a bioslope. First, we need to determine the goals and primary function of the bioslope. A bioslope must be designed for the water quality volume. However, a bioslope can also provide some runoff reduction benefits and potentially be oversized to reduce the required detention volume downstream. Typically, bioslopes are sized for the water quality volume, and a review of runoff reduction credits should also be performed. As we lay out a potential bioslope area, the approach should be evaluated for stability and the location of pretreatment, such as a grass filter strip. Since the primary function for bioslopes are to provide water quality treatment, we will review that portion of the design process first. To size a bioslope for water quality, we'll calculate the water quality peak flow rate using Section 10.4 from the Drainage Manual. This flow rate will be used to size the bioslope dimensions. The water quality peak flow rate is calculated by multiplying the unit peak discharge by area and by the water quality volume. Next, we'll determine the length and width of the bioslope. The length of the bioslope is set to equal the length of the pavement area treated. The width is sized so that the rate of infiltration is at least as great as the water quality peak flow rate. We can calculate bioslope width based on Darcy's law. This equation calculates the necessary bioslope width by dividing the product of the water quality volume peak flow rate, a safety factor, typically 1 for bioslopes, and a conversion factor of 43,200 inches per hour, by the product of the infiltration rate and the bioslope length parallel to the roadway. A minimum bioslope width of 2 feet measured perpendicular to the roadway is generally used for constructability and to facilitate the overall success and long-term operation of the BMP. Now let's step through a design example using these equations. We have an example new roadway project located in Savannah, Georgia. The proposed project includes 200 feet of roadway in length. The drainage area that discharges to the bioslope includes a roadway with 2 12-foot lanes and a 6-foot paved shoulder draining via sheet flow. There is no off-site or bypass runoff. The right-of-way has 25 feet available for a bioslope and pre-treatment filter strip along the length of the roadway. Using this information, let's determine the bioslope width. This project appears to be a candidate for a bioslope BMP, as there appears to be sufficient right-of-way along the full 200-foot length of the roadway to be treated. Additionally, the proposed bioslope has a lateral slope less than 3:1 and a shoulder cross slope less than 5%. Heavy sediment loading is not expected. For this example, some preliminary calculations have already been performed, and it has been determined that the water quality volume is 606 cubic feet, and the water quality peak flow rate is 0.16 cubic feet per second. From this information, we can calculate the bioslope width. Our conversion factor, C, is equal to 43,200, which converts feet per second to inches per hour. The water quality peak flow rate, QWQ, is 0.16 cubic feet per second. For bioslopes, we use a safety factor, or SF, of 1. We use an infiltration rate, K, equal to 10 inches per hour based on media specification and factor of safety. L is the bioslope length parallel to the roadway, which is 200 feet, or equivalent to the roadway length. This gives us a bioslope width of 3.5 feet. Now that the bioslope is sized, we can verify there is adequate right-of-way, lay out the bioslope, and calculate the runoff reduction credited. To calculate the runoff reduction, we'll follow the runoff reduction guidelines from Chapter 10 of the manual. This equation uses the runoff depth for treatment, which is 1 inch for the GDOT-MS4 program, the dimensionless volumetric runoff coefficient, RV, which is equal to 0.05 plus 0.009 times the percent imperviousness of on-site area, and the area draining to the bioslope in acres to determine the runoff reduction volume conveyed to the practice in cubic feet. Using values from previous slides, we have all the data to complete this calculation. Our drainage area is comprised of a 30-foot by 200-foot paved roadway with 100% imperviousness, so we have a volumetric runoff coefficient, or RV, of 0.95 and an area of 0.138 acres. Plugging these values into the runoff reduction volume equation, we calculate a runoff reduction volume conveyed to the practice of 500 cubic feet. Since not all runoff that is conveyed to a BMP will be infiltrated, GDOT has developed some guidelines for runoff reduction efficiencies. We can calculate the runoff reduction volume credited using Table 10.5-1 GDOT BMPs and associated pollutant removals in the Drainage Manual. This table lists the appropriate runoff reduction percentage, or credit, provided by each BMP practice. The percentage of runoff reduction credited is directly related to the soil type. Table 10.5-1 says that a bioslope in A and B hydrologic soils has an RR percent of 50%, so we multiply 50% to the runoff reduction volume conveyed to the practice, 500 cubic feet. This gives a runoff reduction credit of 250 cubic feet. GDOT has developed design tools like special grading plans and construction details, which should be used for all BMP designs. These can be downloaded from the road's website. When using these details, the designer will be reminded of all the inputs required to complete the design, like laying out the underdrain system, providing cleanout locations, and a stabilized underdrain outlet. The construction details include a typical cross-section, plan view, cleanout details, required design data, and design general notes. These elements are necessary to ensure the contractor has all the needed information to construct the BMP properly and conform to GDOT guidelines. Within the Bioslope typical section, the designer should update these details for their project, specifying the filter strip width, bioslope width, and surface slopes. The design engineer is responsible for providing details on the underdrain system, including identification on how and where the underdrain will outlet. The construction details also include guidance for the placement of underdrain cleanouts. Cleanout locations should be specified on the plans and should be spaced no more than 100 feet apart. The construction details should be edited by the designer to include stationing to locate the bioslope and to provide bioslope dimensions, including length, width, slope, and area, as well as media specifications. If you have any questions about GDOT's post-construction stormwater management program, contact GDOT's MS4 Program Manager, currently Brad McManus, in the GDOT Office of Design Policy and Support.